Good morning, students. Today we will discuss the solubility of partially miscible liquids. Now, first of all, what are partially miscible liquids? These are those liquids which dissolve to a limited extent. Okay. For example, we will discuss about the phenol water system. Here, phenol and water, these two are partially miscible liquids, means they dissolve only to a limited extent. So they are known as partially miscible liquids. Okay, when equal volumes of water and phenol are agitated together, we will take phenol and water. When we will take their equal volumes and we will agitate them, then two layers are formed. Okay, one of the saturated solution of phenol in water and another is saturated solution of water in phenol. Okay, two solutions are formed. These two solutions are called as conjugate solutions. Okay, this is the graph of temperature, and on other side its composition. Okay, that is percent by weight of phenol. Okay, in case of phenol water system, means two layers are formed and the two solutions are formed which are called as conjugate solutions. Okay, when these two partially miscible liquids, phenol and water, these are agitated together or mixed together, okay, then we will get solution of different composition. Example, on shaking phenol and water, we get two layers. Okay, first layer and second layer. First layer is a solution of water in phenol and second layer is solution of phenol in water. Okay, with the rise in temperature, when temperature is increased, the water concentration in the phenol layer and also the phenol in water layer increases. Okay, water concentration increases, the compositions of the two conjugated solution becomes nearly same. Okay, their concentration will become same at a fixed temperature. Okay, the composition of each solution is fixed and both the solutions are in equilibrium. Okay, above a particular temperature, such solutions are completely miscible in all proportions. Okay, such a temperature is known as critical solution temperature. Okay, means above a particular temperature, such solutions are, means these solutions become completely miscible in all proportions. So this temperature is called as critical solution temperature or consolute temperature. The upper critical solution temperature, that is TUC, is the highest temperature at which phase separation occur. You can see in the diagram, that is TUC. It is the upper critical solution temperature, means this is the highest temperature at which phase separation occurs. Okay, CST is the critical solution temperature, means this is a temperature above which such solutions are completely miscible. Okay, you can see the graph. Next system is triethylamine water system. Okay, triethylamine and water, these two are also partially miscible liquids. The system is partially miscible above Tk. Okay, this is a Tk, that is temperature, and single phase below. The lower critical solution temperature, that is Tk, is the lowest temperature at which phase separation occur. You can see this graph, temperature on one side and on the other side its mole fraction of triethylamine. Okay, these two are partially miscible liquids. Unlike, as we have studied in phenol water system, the solubility decrease. Unlike phenol and water system, here solubility decrease with the increase in temperature. फिनॉल और वाटर सिस्टम में क्या था, सॉल्युबिलिटी इंक्रीज कर रही थी विद द इंक्रीज इन टेम्परेचर, बट हियर सॉल्युबिलिटी डिक्रीज विद द इंक्रीज इन टेम्परेचर इन दिस सिस्टम. द टू कंजुगेटेड सॉल्यूशन मिक्स कंप्लीटली at or below Tk, means below Tk they both conjugated solution mix completely. This temperature is also referred to as critical solution temperature, okay, or lower consolation temperature. Okay, the determination of critical solution temperature can therefore be used for testing the purity of phenol and other substances. Okay, these are the applications. Next topic is distribution law. Okay, distribution law. Before studying distribution law, I will discuss with you that what is distribution law. For example, you have two solvent, that is X and Y. Okay, you are having a solute A. Okay, according to this law, if a solute A distributes between two immiscible solvents X and Y at a constant temperature, a solute A distributes itself between two liquids in such a way that the ratio of its concentration in two solvents is a constant value. Means A is a solute. Okay, one solute A. Okay, two solvents we are having X and Y. So A will distribute itself in two solvent, that is X and Y, in such a way that its concentration, that means concentration of A in these two solvents X and Y, is a constant value, that is C1 upon C2 is equal to K. Okay, yeah, C1 directly proportional to C2. K is a constant. C1 is a concentration of A in X, C2 is concentration of A in Y solvent. Okay, and K is the partition coefficient or distribution constant. It can also be denoted by KD. Now, explanation of this law. I have already told you that A is a solute. Okay, when the distribution of solute A has reached a dynamic equilibrium, the rate R1 at which the molecule of A pass from X to Y. Okay, rate R1 is the rate at which the molecules of A pass from X to Y is directly proportional to concentration in X, that is C1. Means R1 is directly proportional to C1 and R2 is directly proportional to C2. R2 is the rate at which the molecule A pass from the solvent Y to X is directly proportional to its concentration in Y, that is C2. This law states that R1 is directly proportional to C1 and R2 is directly proportional to C2. Okay, where we can write it as R1 is equal to K1 into C1, where K1 is a constant. R2 is directly proportional to C2. We can write it as R2 is equal to K2 into C2, where K2 is also a constant. But at the equilibrium, the rate R1 is equal to rate R2. Okay, we can write it as R1 is K1 into C1 is equal to K2 into C2. Okay, we can write it as C1 upon C2 is equal to K2 upon K1 is equal to KD. KD is the distribution coefficient. Okay, this equation is the Nernst distribution law equation and KD is the distribution coefficient. It is also constant if temperature is fixed. So this is a distribution of explanation of this distribution law. Okay, next, deviation from distribution law. Okay, that what are the deviations from this distribution law which arises? Okay, there are several complications which may arise which would influence the constancy of the partition coefficient. In some cases, deviation from the distribution law occurs if there is alteration in the mutual solubility of two liquids as a result of increasing concentration. Okay, there is alteration in the mutual solubility of two liquids. Okay, secondly, if the molecular state of solute gets changed in two solvents. Okay, the change in molecular state includes when the solute undergo association or when the solute undergo dissociation. These two conditions can occur. Means molecular state of the solute change in the two solvents. Okay, these are the two limitations, or you can say deviations from the distribution law. You can see. Next are the limitations of this distribution law. There are various limitations. First of all, the solute should not react with any of the solvent. Means no interactions should be there between solute and the solvent. Secondly, the solute must not undergo any change in its molecular state. Means there should not be any molecular change in the state of the solute, okay, in the two solvents. That is, it must not be dissociated or associated. Okay, third, the temperature should be constant throughout the experiment. Fourth, solute concentrations are noted after equilibrium is established. Okay, fifth, the solute concentration in both solvent is low. The law does not hold when concentrations are high, means concentrations in both the solvent is low. Concentration of solute, concentration should not be high. So these are the various limitations of this distribution law or Nernst distribution law equation. Okay, now there are various applications of this law. The process is used for separation of organic solvents from aqueous solution, means this process we can use to separate the organic substances from the aqueous solution. Secondly, the principle of distribution law is very useful in metallurgical operation. A popular example is desilverization of lead, that is parquet process. Okay, we can use in metallurgical operations. Third, the distribution law is also useful in studying the complexions or hydrolysis of salt. Okay, and this distribution law we can also use in the determination of association and dissociation. Okay, these are the various applications of the distribution law. Okay, that's all for today. Thank you.